Good morning, everyone. My name is Ivan Keiler, and today I will be talking about neural networks, more specifically some problems that you may encounter when implementing one, as well as ways to optimize your network. So we'll start off just by having a look at the structure of a basic neural network. Shown here, we've got a network with one input layer, three hidden layers, and one output layer. So each layer contains a bunch of nodes, which are then connected by weights and biases. And these are then used to both predict your output, but also to train your network using an algorithm called gradient descent. I will spare you the details of the forward and back propagation calculus and algebra. They can get quite complex, and instead I'll just focus on this equation for today. So the output Z for layer L. We'll specifically focus on the matrix A, which we got by sending the output Z of the previous layer through something called an activation function. So the role of an activation function is to turn a linear input into some other non-linear output. And this is what allows neural networks to solve the complex problems they have become known for. So historically, the sigmoid and hyperbolic tangent functions were used as activation functions. And it's important to note here that they squish your output, your input into an output between the range 0 to 1 or -1 to +1, meaning that no matter the size of the input to these functions, it would always be mapped into these ranges. So at surface level, this almost universal way of suppressing any input into this standardized range sounds great, because we can then use the same mathematical formula to represent a bunch of different things. However, this leads to the first optimization problem we will encounter today, and it's called the vanishing gradient problem. So vanishing gradients occur when derivatives become so small that our weights can't effectively contribute to the network's training. So let's just take a step back and have a look at what's going on our graph. So the further along X moves towards the right, so your right, the closer Y gets to 1. And now also let's just think of a flat horizontal line and its gradient, which would be 0. So in this graph, the closer Y gets to 1, the flatter the curve gets, meaning the closer its gradient also gets to 1. And because Y only approaches the limit of 1, its gradient won't ever be 0, but it would become so small that it is effectively useless. And this is where the vanishing gradient problem occurs. It's so small, it essentially vanishes. So luckily, there is quite an easy solution, and it's called the rectified linear unit or ReLU function. So unlike sigmoid and tanh, it doesn't suppress your input into some range. In simple terms, the ReLU function keeps any input greater than 0 and discards any input less than 0. So because your values don't go through some squeezification, the chances of those extremely small derivatives forming are much less, and that solves our vanishing gradient problem. So at first glance, the ReLU activation function seems kind of great. It not only solves our vanishing gradient problem, but we have other benefits such as much faster learning and a much simpler implementation. There is, however, one practical problem, and that is dead neurons forming. So let's just imagine a scenario where we randomly initialize our weights and biases so that half of them are negative, half of them are positive. And now let's also remember what ReLU does. If an input is positive, keep it. If an input is negative, set it to 0. So with half of our weights and biases being negative, half of them would just be set to 0, and they would just not participate in the network anymore. They become dead neurons. And obviously, that's a problem. So luckily, once again, there is a very simple solution to this, and it's called using Leaky ReLU. So instead of returning 0 for any negative number, Leaky ReLU returns just a very, very small negative number. So this negative number is small enough that it is almost zero, but because it's not exactly zero, it still allows that neuron to participate in your network. So unfortunately, we are not out of the woods quite yet. So because ReLU is unbounded, it means that weights can become so large that they overflow and just once again become unusable. In simple terms, ReLU does not cap the size of an input like sigmoid or tanh. So if x is equal to 10 billion, then it is kept as 10 billion. If x is equal to a half, then it is also kept. Now you can see how this can become a problem when these two values exist in the same network, which brings us to our third optimization problem called the exploding gradient problem. So quite literally the opposite of the vanishing gradient problem. So the solution to this is to use something called timing initialization. So timing initialization just initializes your weights and biases around a normally distributed value determined by the number of nodes in that layer. This has the double benefit of not only solving the exploding gradient problem, but it also further reduces the chances of vanishing gradients from appearing. All right, so now we can move on to some more explicit ways of optimizing your network when training it. So usually we have this thing called the learning rate. It's basically the speed or tempo at which our network learns. It's static, it's a constant. But these optimizers work by making that learning rate dynamic. And we will start with something called momentum, where as with normal gradient descent, we first just calculate our derivatives. The difference comes in with how we update our weight and bias matrices. So these equations here. We calculate like momentum-like components, which are these ones at the top. And we just multiply our learning rate with those. So this method, I guess, is called momentum because you can think of like a ball rolling down a hill. This would be its velocity, and then this, because there's a derivative there, would be its acceleration. And that's it, like as simple as that. That's how momentum works. Very similar to momentum, we've got something called root mean square propagation, or RMSprop in short. The main difference just comes in that your derivative matrices are squared element-wise, so up here at the top, and then when you do your actual weight and bias matrix updates, you just get the root thereof, so hence the name root mean square. All right, so continuing to build on both these methods, we get something called adaptive momentum, or ADAM optimization. So ADAM optimization is basically a combination of the previous two methods, where we both calculate our momentum-like components and our RMSprop-like components, and we combine them in the weight and bias matrix updates. And then just as a general word of advice, whatever, ADAM is actually a really, really good optimizer, and it's really good for a bunch of different things. There is, however, one kind of big issue with ADAM, and that brings us to our final problem for today, getting stuck in a local minimum. So let's just take a step back and remember what the point of that gradient descent algorithm is. So the technical definition, I guess, would be for it to find the global minimum of the cost function. That sounds a bit weird. So it's just a fancy way of saying we want to find a set of values for our weights and biases that produces the smallest amount of error on our training data. So having a look at this weird 3D graph here, we can see that this represents basically the error of our cost function. So when we start out with training, we initialize our weights and biases in such a way that we are randomly off somewhere. And we eventually want to get to the lowest point on this graph, which in this case would be that dark blue hole, whatever. Now that's called the global minimum, and the other dips in the graph are called local minimums. So we navigate this graph using an algorithm called gradient descent, which I've talked about a bit now as well. Now, what happens with ADAM is that it can sometimes reach one of those local minimums a bit too early during training and just never be able to get out of it. So we obviously want to train, get better, but ADAM just gets stuck there. So our network just doesn't learn properly and it just becomes a bit not that good. So as was the case with ReLU and the dead neuron problem, there is luckily a very simple solution, and it's called AMSgrad optimization. So AMSgrad basically just makes a small tweak to the ADAM optimization algorithm. We still compute our momentum-like and RMSprop-like components, but we only update the RMSprop component if the current iteration's value is larger than the previous iteration's value. So that's basically what these two maximums do in the equation. So the small adjustment allows AMSgrad to still have the same benefits of ADAM, so faster learning, but we can now successfully climb out of and find better local minimums. So our network becomes much more accurate. All right, so what do all of these fancy equations mean? Like, what do they do? To put it short and very simply, these equations just allow our networks to train much faster. And because you train much faster, you can become more accurate. And hence, we will have much better performance at the end of the day.